Alright, so with our new topic, we're looking now into outer space, and one of the first things we look at when we start talking about outer space are the sun and the solar systems, and we start to look at where we came from, origins of the universe. We look at where is Earth and the Milky Way galaxy. We talk about a galactic address where we look at the visible universe and the Virgo supercluster, our local group of galaxies, then the Milky Way galaxy, and even within the Milky Way galaxy we have the different arms on there where we're in the Orion arm. Then our solar system and Earth as the third planet from the Sun. And the Sun is where we're going to spend a lot of time in this next video. But before we even get there, we're going to look at uh, the Big Bang Theory. So for origins of our solar system, we start to look at the Big Bang Theory and how the origins of our solar system came to be, or at least our best guess on that. Okay, and the standard theory of that is that it sprang into existence as a singularity almost around 13.8 billion years ago, and I have here a picture of what the TV show The Cosmos uses as its universal calendar or galactic calendar, as we look at the things that started over here as a Big Bang, and as things go on, we start to get to our first big stars, and then we start to get to galaxies forming, and then from there our own Milky Way galaxy, and then within the Milky Way galaxy we get to our sun forming, and then the Earth and other objects on there. With this Big Bang Theory, it's not like there was an explosion, but more of a expansion, almost like a balloon popping or a water balloon, and it's spilling out that water or pushing that water out as it expands or releases that contents through the universe until it gets to the current size that we see it today. And as far as we know, we still see the universe as expanding. Doesn't seem to really be slowing down at all. Okay, and with this Big Bang Theory, okay, we look at some of the things that have happened throughout this theory, and some of the things that happened in the very, very beginning. And atoms started to kind of break apart or into pieces, and then they started to cool and slowly start to come together. And then finally we get stars forming. Then we start to get clumps of stars, which would then lead us to galaxies. And then finally we get to where we are currently today. So we look at the universe starting 13.8 billion years ago. About 13.5 billion years ago, we look at the first stars being born. That's important with these first stars because they are so massive. They're going to lead to the formation of a lot of heavy elements. When we look at a lot of heavy metals, even some of our other elements other than hydrogen and helium coming out of these first stars. And these first stars were so massive they did not live for a very, very long time. Kind of like often referred to as titans. Because of their massive, massive size, they would have lived for only a short period of time on the order of stars. Where our sun is projected to live for 10 billion years, these stars would only live for a few 100,000 years or maybe a million years, which is much, much shorter. Because they are bigger, they're going to burn through their fuel a lot faster, and they're going to lead to the creation of other stars. And when other stars are born, that's going to then cause them to group up into areas, and we're going to start to get our first galaxies. And after that, we eventually get to our own Milky Way galaxy, forming about 11 billion years ago, BYA. From there, we're going to start to look at the origins of our own sun. And with the origins of our sun, we start to look at some of the order of events that happened as our solar system started to form. And I'm going to go into these in a little bit more detail, but we have essentially 10 steps that we looked at in class for our solar system forming, starting with a nebula, and then having their solar system start contracting and heating and getting into a disk, so that gas starts to form into a shape. The sun turning on, condensing, accreting rocky planets, gas giant planets, and then flinging and orbiting. So as we zoom in a little bit on these, okay, we kind of look at a nebula. This is the remains of old stars. When they finally reach the end of their life cycle and they explode, they release a lot of gas and dust throughout different parts of the universe, and they even have here highlighted a protostar. That's where we believe that a new star is going to form, and maybe even a new solar system from that nebula cloud or the remains of older stars. As they start to contract, they start to heat up. Some friction and different things is going to start to take place, and we're going to start to get some orbiting. Gas and dust will start to kind of clump up and group up together. As they clump up and start to group up, that contraction starts to happen a little bit faster. There becomes a little bit of rotation or organization in the center, and we start to see temperatures start rising in the center of that. When we start to get to a disk shape, we almost start to get to a protostar here. We're not quite at a star formation yet. Temperatures are still very low, and most importantly, fusion has not yet started. But we start to get that cloud of gas that was just in a irregular shape now into a gravitational pull, where it's now given it some shape, and it's flattened it out, and now it has some organization to it. From there, we start to get the sun turning on, or any star that would go through this same process. And that's going to be important because we need something like the star. And they have here highlighted when two hydrogens are going to start to fuse together in the core of the star. That's when we're going to say that we have a star, because when fusion takes place, that's when light and heat are going to be given off by that star. So they have here a big change in temperature from before, where it was only around 3,000 degrees Kelvin, to up to 10 million degrees Kelvin. After that, we're going to start then looking to see the planets and other objects starting to form. So we're going to get some of the remaining dust cloud and gas cloud starting to condense, and we see that it is hotter closer to that star or sun in the center, and it does get colder. They have here the snow line where we start to get ice crystals forming as well. And then we get what they call here accreting, where we start to get planetesimal size objects, or objects that are closer to the size of planets, now starting to form, where a lot of that gas and dust is going to start to group up and become close to planet-size objects. And as we talk about planetesimal size objects colliding, with a little foreshadowing, that's what we're going to talk about as we talk about the moon in the next section, and origins of the moon, with planet-size objects colliding, and different theories about how we got a moon to follow around the Earth. We're going to look at the next two things, which are going to be rocky planets forming and gas giant planets forming. Again, a lot of these things are going to happen at similar times. I have here rocky planets slightly ahead of the gas giant planets forming. They're a little closer to the sun. There's a little less area for them. They're going to orbit around the sun faster. Their orbits aren't as big, so they're going to be able to clean up some of the area that they have to, and get a lot of that dust, dirt, and rock out of their way. Where our gas giant planets have a lot more area to cover, even though they are larger with greater gravities, it is going to take them longer to make their way around. And then finally, as we get things pretty much fully formed, we get to almost a current solar system picture here, where we have the planets pretty much fully formed, orbiting the sun, and I have here flinging or orbiting for this one, as we get to some objects that would be in the outer solar system, maybe moons of some of these other planets as they're coming close to their planets, like especially with Jupiter, some of these planetesimal objects, or Plutoids, objects that aren't quite the size of planets, maybe flung off as moons at one time, or satellites of those planets and now are orbiting in the outer parts of the solar system. Possible explanations for areas or objects like Pluto, Ares, Hermes. Some of these, like I said, Plutoids are formerly called dwarf planets. So we start to look at that formation of our solar system. So we go over some of the things for the origins. We look at about 5 billion years ago, this cloud of gas coming down and the particles in the center becoming densely packed together, and they start fusing together. This fusion process is going to release tremendous amounts of heat and light, which are going to combat the force of gravity. And eventually we're going to get those forces to reach what we call equilibrium. And when they reach equilibrium, gravity is not going to really compress it down anymore, and fusion is not going to be able to push it apart anymore, and they're going to reach a kind of stable balance between gravity trying to crush it and fusion keeping it at the size it currently is. So there'll be a constant or consistent amount of fusion taking place inside the sun. So that balancing between those two forces. We refer to that as a star. We start to look at the size of the sun. Okay, and some of the different facts about the sun. It's about 150 million kilometers away from Earth. We refer to that distance as what we call an astronomical unit. With an astronomical unit, we're going to use that distance for a lot of things within our own solar system. We'll say things that are other planets maybe are 1 or 2 or parts of astronomical units away from Earth or away from the sun. So we kind of use that common distance that we have from the Earth to the sun to kind of gauge how far other objects in our solar system are away. One of the other big units that we use when we're talking about outer space is a light year. When we get outside of our own solar system, we measure things a lot in light years because the numbers get very, very large. So we look at the distance that light can travel, and I have just some information about how fast light does travel. Once light makes it to the surface of the sun, it takes about 8 minutes to get from the surface of the sun to Earth, and I have here it's traveling at 3 times 10 to the 8 meters per second, or 186 miles per second. And I put up in here that it travels 5.865 trillion miles in a year. And since most of you are about 13-year-old in the 7th grade, give or take a little bit, light while you were on Earth would have traveled approximately 76.254 trillion miles. And obviously that's a rough estimate. Looking at the size of the sun now with its diameter, okay, it's about 1,400,000 kilometers for its diameter. If we were to move the moon 3 times as far away, the orbit then of the moon would be roughly the circumference of the sun. So just to give us an idea again of the size of the sun. Okay. One of the important things that we have to remember is that the sun is not a large star, it is only a medium star. So as we talk about that in comparison to other stars, here's a picture of our sun and the Earth and some of the sun and some of the other planets there. And maybe not all these proportions are completely 100% on, but they are very, very close. The sun is by far the most massive object in our solar system. It takes up 99% of all of the mass of our solar system. So all of the other planets, moons, satellites, comets, everything on Earth is less than 1% of the material in our own solar system. As we start to compare the sun to other stars, okay, there are some massive stars, a lot of them being red giants, but our sun very, very small in comparison to them. And we look at some of the other massive stars that are in our solar system, okay, and we can compare them, this one being our sun here, this tiny dot, in comparison to some of these others. Betelgeuse being one of the red giants that are somewhat close to us in our own Milky Way galaxy. And that's where we're going to stop for now. If you have any other questions, please see me in class.